In this video, we're going to continue our discussion about taking derivatives using the chain rule. And we take derivatives using the chain rule whenever we're dealing with composition functions. So let's think about what we have or what we're looking at here. In this problem, we have the volume, V of R, and the surface area, S of R, for some Jawbreaker piece of candy, are given if we know the radius, right? So volume in terms of the radius is 4/3 pi r cubed. That's the formula for the volume of a sphere. And surface area in terms of radius, the surface area for a sphere is 4 pi r squared. So Roger Guffey, this dude, estimates the radius of a Jawbreaker while in a person's mouth to shrink at this rate. So the radius, if you're sucking on a piece of candy, it's getting smaller. So the radius shrinks. Radius in terms of time t is 6 minus 3/17 t. So r of t is a function radius in millimeters after t minutes. Let's find the life expectancy of a Jawbreaker. So in order for us to find the life expectancy of a Jawbreaker, this is really just an algebra problem. Because if we know the radius is 0, if the Jawbreaker has disappeared, then we know that the Jawbreaker is gone, and we can determine the time by solving that basic equation. So if I say for part A, 0 equals 6 minus 3/17 times t, then that is 3/17 t equals 6, or t equals 6 times 17/3. We can reduce that, so that's 2 times 17, or t equals 34. Since t is measured in minutes, we know that the Jawbreaker is likely to last for only 34 minutes. All right, so let's find dv dt and ds dt when t equals 17, and we'll interpret our answer. So dv dt and ds dt, those are derivatives. And a derivative is a rate of change. Here we have volume with respect to time, or surface area with respect to time. Now, if we look at the formulas given for volume and surface area, they are not with respect to t as the independent variable. They are with respect to the radius. However, what we can do here for part B, and we're going to do this twice, is we can find that composition function. So V of R of t is 4/3 pi times 6 minus 3/17 t, quantity cubed. And S of R of t, my surface area formula is 4 pi r squared. So that would be 4 pi, and then my r, 6 minus 3/17 t, quantity squared. So these represent my composition functions, and now I have volume in terms of time t, as well as surface area in terms of time t. So I'm going to find the derivative of each. And because these are now composition functions, I need to use the chain rule. So the derivative of v with respect to t, well, this coefficient 4/3 pi, remember pi is a number, so 4/3 pi is a constant coefficient that will remain. And we'll take the derivative of this. So finding that derivative, that's going to be 3 times 6 minus 3/17 t to the second power. So I used the power rule. The 3 came in front. I subtracted 1. But because this is not just t on the inside, we also need to take the derivative of the interior. The derivative of 6 is 0, and the derivative of negative 13 or 3/17 t is going to be minus 3/17. So I'll just clean that up and write negative 3 over 17. So this is my derivative. Now, I can tidy this up a little bit because that 3 and that 3 will cancel. So my dv dt formula, the derivative of the volume with respect to the time, is going to be negative 12 over 17 pi times 6 minus 3 over 17 t quantity squared. So I just took that 3, multiplied it by the 4, and brought 17 in front. So if we want to find the volume at time t equals 17, that just means I'm plugging 17 into this function. So dv dt at t equals 17 is negative 12 over 17 pi times 6 minus 3 over 17 times 17 quantity squared. See, those 17s cancel. 6 minus 3 is 3. 3 squared is 9. So I have negative 12 over 17 pi times 9, or negative 108 pi over 17. And we can write that as an approximate value. Typing that in my calculator, I get negative 19.958353. And the decimal continues going. So this is an approximate number. Whenever we take a decimal that's not truncated out of our calculator, that means those digits likely keep going, and we are now approximating when we cut off and round. So what does this mean? Remember, this means volume with respect to time. Now, in this problem, volume, since we're dealing with millimeters, volume would be millimeter cubed per, since time is measured in minutes, the unit here would mean it's shrinking at a rate of about negative 20 millimeters per minute. And that's the rate at which that would be millimeters cubed per minute, because volume is going to be a unit cubed. So millimeters cubed per minute, and that is the rate at which the volume is shrinking. So let's repeat this problem. Let's repeat this for surface area. So I've written my exact answer, which we said was roughly negative 19.9. And that's millimeters cubed per minute. So for surface area, we're going to do the same thing. We're going to differentiate and find the derivative of surface area with respect to my independent variable, t, time. So again, treating 4 pi as it's a constant coefficient, and taking the derivative of 6 minus 3/17 t quantity squared. That would be 2 times 6 minus 3/17 t. That would become to the first power. And then taking the derivative of just the inside, the derivative of 6 is 0. And the derivative of negative 3 over 17 t is negative 3 over 17, which cleans up to just negative 3 over 17. So if I look at 4 times 2 times 3, we can say that ds dt, 4 times 2 times 3, that's 8 times 3, we've got negative 24 pi over 17 times 6 minus 3 over 17 t to the first. And of course, we do not need to write that to the first power. So if I go and again come back up here and evaluate that when t is equal to 17, that's the derivative of s with respect to t evaluated at t equals 17. That's negative 24 pi over 17 times 6 minus 3 over 17, plugging 17 in, times 17. We see those 17s cancel. 6 minus 3 is 3, and 3 times 24. ds dt at t equals 17 is equal to negative 72 pi over 17. So this is the rate at which the surface area is shrinking. Now, if we think about our units here, we have S over T. S is surface area. Area is units squared. So we have millimeters squared per. So surface area over time. Time is in minutes. So millimeters squared per minute. Getting an approximate value in our calculator, I have negative 13.305568889. Or we will say that the surface area is shrinking. We know it's shrinking because it's negative at a rate of about negative 13.3 millimeters squared, surface area units per minute, time units. So the exact answer here would be negative 72 pi over 17, which is, again, of course, approximately negative 13.3 millimeters squared per minute. So we see that both the volume of the Jawbreaker and the surface area of the Jawbreaker are shrinking, and they're shrinking at different rates. All right, so I hope that helps you understand this problem. Please let me know if you do have any questions, because I'm here to help.